All right, the speed of sound. Look at that fast playing. That's some quick old playing. Something that we know is this: as at high temperatures, air molecules move faster. So we kind of know that for anything really. As you increase the temperature of a substance, its molecules vibrate or move around faster. That's true for air molecules as well. If sound is just the movement of those air molecules, it's got to be a certain pattern or vibration. But as those air molecules move faster, sound is going to travel faster. So on a warm day, sound actually travels just a little bit faster. Probably not enough for you to really notice, but the warmer it is, the faster it goes, the sound goes. Something that we know is this. At 0 degrees Celsius and 101 kilopascals, that's air pressure, that's kind of standard atmospheric pressure, sound travels at this, 331 meters per second. For every increase of temperature, so for every degree Celsius of increase, sound travels just a little bit faster. Now, if pressure changes, sound speed is going to change as well, but we're not going to focus on that. We're just going to focus on temperature. So here's a little equation for you. At 0 degrees Celsius, that whole thing goes away. Sound travels at 331 meters per second. For every 1 degree Celsius of temperature increase, sound travels 0.59 meters per second faster. Okay, so the speed here is speed in meters per second. Temperature is in degrees Celsius. All right, so let's try this out. If the speed of sound is measured to be 328, okay, so V sound, 328 meters per second, what temperature is it? And we know speed of sound, goes according to this little equation right here. If we know that the speed of sound, so V sound if you want, is 328, then we can just go ahead and sub that number in, and we're going to solve for temperature. So let's try this. 328 minus 331, negative 3. Whoops, I forgot my 9 right there. 0.59 T. Divide by 0.59. Temperature, it's approximately 5.08, 85, I guess. So temperature, approximately negative, I guess 3 sig digs. 5.0, it actually would be 5.08. Let's get good sig digs here. This would be a 4, this would be a 7. So 5.08 degrees Celsius, but negative. So the equation works whether we're talking about positive temperatures or negative temperatures. This thing here, it is below 0 on whatever day this is. Reflections of sound are called echoes. We've heard this term a lot. Reverberation is when these echoes or these notes that you make kind of gradually fade away as they echo back and forth. You'll hear echoes in like the stairwell. If you walk into the stairwell at school, especially if it's empty, as you walk in there, if you make a sound, it kind of like slowly fades away, as opposed to if you're in a small room like a closet, especially if there's lots of clothes hanging, the sound kind of is very dead. It sort of fades away very quickly. A lot of people, if you're into podcasts or anything like that, a lot of people build their podcast studios in a closet just because of the sound quality in there. The sound is very dampened, especially if there's carpet on the floor or fabric on the walls. SONAR is probably something that you've heard of. It actually stands for something. It's sound navigation and ranging. If a short pulse is emitted, we know how fast it travels through air or water or whatever. SONAR is often in water. How fast that sound travels. So a short pulse is emitted, and then the time it takes for the echo to return is measured. The distance, then, we can figure out how far away the object is, whatever object the sound bounces off of, by knowing the speed of sound in water. So in water, it's typically called sonar, but really the same thing happens with echolocation, if you've ever heard of that. That's what bats use as they fly around. They use echolocation. Same idea. They make a sound. The sound travels out. It bounces off some object and comes back to them. And based on how long it takes that sound to come back, the bats can figure out, with their tiny little calculators, they can figure out how far away the object in front of them is. Here's like a boat doing it, right? If they want to know how deep the water is or something like that, the sound goes down like this. it comes back up. It can go straight down and straight back up, but just to kind of keep it on an angle so we can see it. Based on how long it takes, we can figure out how deep the ocean is or the lake or whatever. Just notice that the sound has to go all the way down and all the way back up. So the distance that it's covering is actually twice the depth. So if you go through and do this calculation and solve for the depth, you're actually going to get twice the depth. You're going to get the full sound journey. We actually only want half the depth if you're trying to figure out how far away something is. Okay, so that's important to remember. Last thing in here, I think, Mach number. You've heard of, like, I don't know, a plane is traveling at Mach 3 or something. Or maybe you buy your Mach 3 razors. Mach number is the speed of the object divided by the speed of sound. So for the most part, we never travel at these kind of speeds, but if something goes really, really fast, maybe twice the speed of sound, then it's traveling at Mach 2. Okay, so just a quick example here. If an airplane is traveling at Mach 3 in 0 Celsius air, how fast is it going? So let's try this. If it's going at Mach 3, it's going exactly 3 times the speed of sound. So first of all, we got to figure out what is V sound. Okay, so V sound we know, it's 331 plus 0.59 T. If we're told it's 0 degrees Celsius, that whole thing goes away. So speed of sound is just 331. Then we know our Mach number. Mach number is V object over V sound. We know that the Mach number, the Mach number in this case is Mach 3. The speed of sound is 331. We can multiply those things and we can figure out the object is going at 993 meters per second. I'm not totally sure what the sig digs are here. I don't know if it's 1 sig dig. You could say it's about 1,000, but I'll leave this with no sig digs. The object is going about 993 meters per second.